To wrap up our unit on prediction, this video is going to focus on one really important property, which is the symmetry of prediction. Now, there are kind of three bits that we're going to go into. So first, we want to be able to define the symmetry of prediction informally and formally. And then we want to have some kind of understanding of how to demonstrate this property by combining plots that show that in cases where x predicts y, then y also predicts x. So defining this property informally is really easy, and in fact we've already done it. So it's just that if one variable predicts another, so if x predicts y, then it's necessarily the case that that second variable predicts the first. So in the case of baby clothing predicting gender, if it's the case that a baby's clothes predict gender, then the baby's gender necessarily predicts the color of clothing that they're wearing. So the formal definition of this property looks a bit complicated, but let's take it in parts. So really this just has two pieces that should both be a little bit familiar. So this first bit before the implication arrow is just our usual formal definition of a variable x predicting a variable y. So we say that if there are two different x values that result in different probability distributions of y, then we say that x predicts y. And then similarly, this second line is just the same idea, except we've swapped the x's and the y's. So here we're saying if there are two different values of y that have different or mean different probability distributions of x, then we say that y predicts x. And putting all of this together, this implication arrow just means that if it's the case that x predicts y, i.e. if this first bit is true, then it's necessarily the case that y predicts x. Now, demonstrating this property is beyond the scope of this class, but the important thing to remember here is that this symmetry of prediction just follows directly from our formal definition. Now, the last bit is demonstrating this property. So here, we talked previously about how to create plots to assess whether one variable predicts another. So demonstration for our purposes is just going to be understanding which plots to put together in order to show that x predicts y and y predicts x. So in order to do that, let's go into R and let's load the VGAM data library. And here we're going to use the UGSS dataset. Now, if you check out the documentation here, this dataset is really interesting. This is or carries some information on a survey of undergraduate students on just a ton of different variables. So we've got information about gender, age, and then a bunch of cool things like whether they have piercings, if they have tattoos, how often they see movies, what sports they like, what their income, what their rent is, etc. So this is a fun data set to kind of investigate a bit. So here we're going to look at two variables. So one is going to be, I think it's called tattooed, which just tells us whether a particular respondent has a tattoo. And then the second variable is called fruit. And students were just asked what their favorite fruit was, and there are maybe 13 to choose from or something like that. So this is an example of two variables that we wouldn't usually guess have a predictive relationship, but it turns out that they do. And in order to see that, we are again going to use this plot table approach, and because these are both categorical variables, this will help us determine whether these variables have a predictive relationship. And now if we look at the plot at the right, we can see that the axes are a bit jumbled. So I'm going to go ahead and use this par LAS command. And once I've entered that, if I rerun the plot, it'll just flip my axes here to make this a bit more readable. So let's talk about this plot briefly. So remember that when we're looking at or looking for a predictive relationship between two categorical variables, we're talking about the variable that's on the x-axis predicting the variable that's on the y-axis. So here, the x-axis tells us whether or not people have tattoos. So we can see that kind of the majority here of our respondents do not have tattoos. And then these columns here tell us that within some response on tattoos, what is the distribution like of favorite fruits? So we were saying before that the way to see that whether or not an individual is tattooed predicts their favorite fruit is that we don't have perfect alignment of these vertical breaks. So for example, if we look at students who have tattoos, we can see that proportionately they are way more likely to list strawberry as their favorite fruit, which is something that's not very intuitive, we wouldn't necessarily expect. And then similarly, if we look up here at banana, we can again see that tattooed students are much more likely compared to students who do not have tattoos to report that banana is their favorite fruit. So the idea here is that if we know someone is tattooed, i.e. we know that they're in this column, then we can predict their favorite fruit. Not with certainty, but knowing that they are tattooed changes our probability distribution over their favorite fruit. Now, to demonstrate the symmetry of prediction bit, I'm just going to copy this same command, and here, rather than listing tattooed first, I'm going to list fruit first, and then tattooed second. So when we look at this plot now, remember again that so with these plots, we're still using the variable that's on the x-axis to predict the variable that's on the y-axis. So by flipping these around, we're now asking whether knowing someone's favorite fruit helps us predict whether or not they are likely to be tattooed. So here, we can just look at apple and banana as an example here. So if we know that someone likes apples as their favorite fruit rather than bananas, we know that they are less likely to have a tattoo because these vertical breaks are not in the exact same place. Now, this plot that we've made in conjunction with the first plot that we were looking at together show this symmetry of prediction. We know just from looking at the first plot that because being tattooed predicts favorite fruit, we know before we even look at the second plot that knowing favorite fruit predicts whether or not someone is tattooed. So to, again, return to the points that we were going to cover, we talked a bit about the definition of the symmetry of prediction in both an informal and a formal sense, and then we talked a bit about how to actually demonstrate this property using pairs of plots.